So today I'm coming to you from a bowling alley, right? Not really. This is one of my fun Zoom backgrounds, but a bowling alley is the backdrop for my story today. So this was way back because it was before I started at the college. I think it was the winter of 2006. Okay. And it was February break, and my kids were young, and we were just all sitting around bored. And my husband went and played racquetball up in Rochester. So we live in Geneseo, and he was up playing racquetball in Rochester. And so he's driving home and he sees a sign on a bowling alley that says February break 50-cent games. Okay. And so he came back home and said, well, hey, let's go bowling. And so we made a special trip to Rochester, right? We kind of planned our day. There's a bowling alley in Geneseo, but we planned our day because there's this special up at the bowling alley here up in Rochester. And when he told me 50 cents a game, I did say, that seems awfully cheap, right? That seems almost a little bit too cheap. Like my mother always had this saying that if it sounds too good to be true, it probably is. So I said, well, I'm sure there's a catch. Like they're going to charge you an extra dollar or two for shoes, or, maybe it really is 50 cents a game. And they're just hoping that if they get you into the door, you'll pump quarters into their arcade and you'll buy their overpriced pizza and their overpriced soda. And, they're just trying to get you into the door to spend money in other ways. All right. So I was a little bit suspicious that it almost sounded too good to be true. So anyway, we get up there and we walk in the door, and then the manager tells us that, or the cashier tells us that there is a $5 cover charge per person, and then it costs 50 cents a game. Okay. I would have even been okay if they had said like, well, your group has to pay a $5 cover charge, and then after that it's 50 cents a game. All right. That to me, that would have been reasonable, but a $5 cover charge per person. And so if we were in class, I always ask students, like, raise your hand if you've ever paid a cover charge at a bowling alley. I mean, there's bowling specials. Like my husband and I used to always, when we were dating in college, we would always go to like Rockin' Bowl at midnight. And it was like, pay a flat fee and bowl as much as you can in those 2 hours. Okay. So, there's often things like that at a bowling alley where you pay a flat fee and then you get a certain set amount of time to bowl. But a cover charge, and then you start paying your cost per game. So I had never heard of that. Usually when I ask the class, when we're in class, I'm asking the class this, and it's the same response. Everybody's like, no, who pays a cover charge at a bowling alley? Now, if I were going to a bar and it said 50-cent drafts, I would know that I was paying a cover charge. So we were not very happy. And we talked to the manager and we said, listen, your sign says 50-cent bowling. Right? It says 50 cents a game. And the manager says, well, yes, but if you bowl a lot, it's a very good deal. If you bowl a lot of games, this is a good deal. And we said, yes, we understand that. However, your sign said 50 cents a game. No matter how many games we bowl, we are never going to pay 50 cents a game. And that's what the sign said. So we felt like we had very much been misled. We felt very much like that was false advertising. So here's what I want you to do. We're going to examine my claim that no matter how many games we bowled, you would never pay 50 cents a game. And so let's take a look at this. We're going to write an equation, and then we're going to look at it graphically. So let's let x equal the number of games bowled. Actually, let me switch to a text box. It's easier. Number of games bowled. And I want you to write a formula, not for the total amount of money that we're going to pay, but the average cost per game. Okay, let's write that into a formula. So pause the video and try to do that. Okay, write the formula for the average cost per game. Okay, so if you're back, people will often write this. They'll write the $5 and then the 50 cents per game bowl, so 0.5x, all right? That would actually equal the total amount of money that we would spend bowling X games, okay? And this is per person. I probably should have said that. Average cost per game per person, okay? This would not be the average cost though. If I found the total cost, so if I ended up spending, you know, $13 total cost, to find the cost per game, you'd have to divide by the number of games that you bowled. Okay, so this needs to be the formula divided by X. And then if I want to simplify that, okay, this is a sum. So if I divide by X, I have to divide into each term of the sum. All right, so then my formula for the average cost per game could look like this. 5 divided by X plus 0.5. Okay, so I'm going to enter this into my calculator. So bear with me, it always takes me that minute to share my screen. And I have the 84 pulled up here today. Okay, since that's what I know most of you have. So before I look at the graph, I want to consider what is a reasonable range and domain. Okay, so that will help me set my window. So how should I set this window? I can't bowl a negative number of games, right? I'm not going to bowl 0 games. So I am going to start this at 1, right? 1 game. And maybe we'll look at bowling 1 to 10 games. All right, now what should Y be? Y is the average cost per game. Okay, I'm going to set my Y at, my Y min at 0. Oh, wait, bear with me here. I try to always go to my keyboard and do this, and I have to remember I can only manipulate on here. The highest cost per game that I'm ever going to pay is for that first game that costs $5.50, right? Because when I only bowl 1 game, I'm paying $5.50. Okay, so there's my window. Wait, I don't want that second 6, just 1 6. So we'll start at 6. All right, so let's look at this on graph. And oh, I have a table over here. Let me go to table set, and let's just sort of look at it on normal. Sorry, bear with me again. Let's start at 1, okay? And then look at the graph. No, why did it not save? Table set, start at 1. I probably have to hit enter. There we go, have to hit enter. Now look at it on the graph. Oh, I'm sorry, I know what the problem is. I have it set on ask and I want it to be on auto. All right, sorry about that. Thanks for bearing with me. All right, now look at the graph. Okay, there we go. That's what I wanted to see. The cost per game from 1 to 10, okay? And as I can see, you know, if I bowl 10 games, it's quite a good deal, you know, $1 per game. I also noticed that the cost per game changes. Look how steep I am right in here, right? So the amount I save per game if I keep bowling. So in the early stage of this, I should be like, hey, I should bowl another game because I want to lower my cost per game. I want to get the most for my money, right? Whereas by the time we get to like 10 games, you know, my hand's getting tired and I'm probably like, okay, it's $1, about $1.05 per game. If I bowl 9, it's $1 per game. If I bowl 1, about 95 cents if I bowl 11. So like I start to see that kind of diminishing returns thing happen. Okay, but remember what my argument was to the manager. I said to the manager, no matter how many games I bowl, I am not ever going to pay 50 cents a game. And that's what your sign said. So that's why I'm angry and feel like I've been misled by your sign. So let's take a look at what would happen if I did start to bowl like a ridiculous number of games. So let's go back to table set, and I sort of gave it away by having it already on there, where we were looking at things like, what if I bowled 100 games? Nope, let me go back. Y equals graph. Wait a minute. I want to enter into the X column table. There we go. All right, I'm not totally used to this, so thank you for bearing with me. I could always make the video over again, but then I'd have to redo the whole beginning. So 100 games, I'm getting closer, right? If I bowled 100 games, now I figure that you could bowl maybe about 4 games in an hour, right? If you were bowling, maybe 5, but at a rate of 4 games per hour, that's 96 games in a 24-hour period if I didn't take any breaks for food, restroom, or sleep, right? So this would be more than a day of consecutive bowling. I'm getting closer to the 50 cents a game. Well, what if I bowled 300? All right, not rounding off to 50 cents yet, but I'm getting closer and closer. So we can see that I'm approaching 50 cents, right? As time goes on. And so about 100 games in a whole day, right? So 500 games, that would be 5 days of consecutive bowling with no sleep, no bathroom breaks, no food. I'm getting closer. I think by the time I bowl 1,000 games, don't even round off yet, right? I round off to 51 cents, okay? So as you can see, my argument to the manager was that no matter how many games I bowled, I'm never going to get to 50 cents, right? Now, maybe around in here, I will actually round, like that rounds to 50 cents, okay? And so what I can see happening is there is this value, and this would be known as the horizontal asymptote line, okay? This value of 50 cents, if I put that on my graph, and I'm actually going to change my window here to go out to like 50, okay? What I want you to notice is there's a horizontal asymptote line of 50 cents on my graph. So that means that I am never going to hit 50 cents, but as time goes on and on and on, and keywords here are time is going on, right? So I could say something like, as X approaches infinity, right? As if when I start bowling like 2 weeks straight with no breaks, no sleep, right? So I let that number of games approach infinity, then I get closer and closer to the 50 cents, but I never reach it. So let's go here and write some of that in symbols. Okay, so what I can see here is that, I'll erase over here. Okay, what I can see with this is that if I came in front of it and I wrote the, oh my goodness, draw, select, gracious. I'm still getting comfortable with some of these tools. If I wrote the limit as X approaches infinity, time goes on and on and on and on, then I approach but never reach 50 cents. So remember, we saw that in the last segment with limits, that we get close to a value, but we never actually achieve that value. All right, so this would be the limit. And I always tell students, you know, tell me what is happening here and forget the math, right? Use common sense. What is happening when I do the 5 divided by the X, okay? And what is actually happening is that $5, as I divide that up by more and more and more and more games, this ratio, this quotient becomes less and less significant. If I bowl 1,000 games, 5 divided by 1,000 is very small. So that this, as X gets large, this part actually goes to 0, okay? And another way that I describe this is often I'll look at ratios like this, and I'll talk about the cookie concept, okay? So if we're looking at what happens as X approaches infinity, and we have a fraction, we can think about a race between the numerator and the denominator, okay? So if I'm thinking about the cookie concept, okay, where the numerator, because to understand fractions back in elementary school, your teacher might have helped you understand like x over 8 or 8 over 3 by saying there's 8 cookies, there's 3 people. How much cookie does everyone get? Okay, if I were looking at a ratio like this, and I said, okay, this numerator is the number of cookies that we have, okay? This denominator is the number of people showing up to eat the cookies. Well, if I were to look at these functions graphically, the first one is a straight line. In the beginning, right, these two functions would be pretty close together, but what happens is as time goes on, x squared leaves x in its dust, right? Because this would come and like this would go all the way up, like through the ceiling, like this grows much, much faster than x squared. And so if I were to talk about the cookie concept, the numerator is the number of cookies, that's growing much slower than the number of people showing up to eat the cookies. Okay, so then how much cookie does everyone get? Everyone would get less and less and less cookie. And so eventually we're only getting crumbs of the cookie. Okay, so this limit would be 0. Whereas if I had a situation like this, all right, the limit, x is getting large, and the numerator grew faster than the denominator. Okay, so say, and I would refer to this as, sorry, this should be infinity. I would refer to this as a top-heavy fraction. Okay, say the numerator was growing faster. That means the number of people showing up to eat the, or number of cookies, numerator is the number of cookies. The number of cookies is growing faster than the number of people who show up to eat the cookies. That means as time goes on and on and on, I'm getting more and more and more and more cookies growing much faster than the people showing up to eat the cookies. So everyone who shows up gets more and more and more cookie. All right. Now, if I had this situation where the numerator and the denominator grew at about the same rate. Okay, so they're growing at the same rate. So I have, you know, because the degrees are the same. So I have like 3x plus 1 over plus 1 over like x minus 5. For the most part, the numerator is 3 times as big as the denominator. Right? Therefore, there's 3 times as many cookies as there are people showing up to eat the cookies, right? Which means at the end of the day, everyone, because these are growing at basically the same rate, right? But this is just always 3 times bigger. That would mean that everyone showing up would get 3 cookies, and that would be consistent even as the number of people and the number of cookies grew, okay? Because they're growing at the same rate. And with the 1 and the 5, now when x is small, 1 and 5 are significant, okay? And I always ask students, I say to them, how many of you, if you had $5 in your pocket and it dropped out and fell on the floor, how many of you would be upset and you realized you lost it, all right? You lost $5 that was in your pocket. Right? And pretty much everybody would nod and say yes, because you guys are poor college students, right? And so $5 for you is a, you know, a soda and a piece of pizza. I don't know if you can even still get that for $5. But anyways, for you, it's significant. Now, there is a saying that if you look at like a billionaire, like Zuckerman or like Tom Golisano or Bill Gates, somebody like that who is a billionaire, even Donald Trump, I guess we'd have to say that about him. The saying is that if one of them dropped a $100 bill on the floor, that in the amount of time that it took them to reach over and pick up the $100 bill, they would have already earned more than $100 in that matter of seconds that it took them to pick it up. All right, because if you took their annual salary and you divided it up by seconds, they would earn more in the time that it took them to pick up the $100 bill than the 100 is even worth. So that means that if they drop a $100 bill, they shouldn't even bother picking it up. okay? That's because they're billionaires, right? So if you have a huge amount of money, you don't care about insignificant quantities like $1 or $8, or, you know, 1 or 5. So when X is small, you know, it matters. Like if we're looking at graphing from 0 to 10, if I told you to graph y equals x plus 5, and you said, nah, I'm just going to graph y equals x, right? That would be significantly different if you were graphing from like -10 to 10. Now, if you were graphing from 0 to a billion, and you said, I'm just going to leave out the 5, right? As x is large enough, this 5 becomes insignificant. These two functions, when x is large enough, there's really virtually no difference between a billion and 1,000,000,005. Okay, so as x is large enough, these quantities become insignificant. All right, and so that would allow me to, if I were looking at something like this, find the limit as x approaches infinity of, let's say, x squared minus x plus 5, and in the numerator I have x plus, or x minus 10, okay? So x is huge, right? Or in other words, I am a billionaire. So I really don't care about $10 or $5 because I'm so rich, all right? So I say, well, those are insignificant, right? And then I say, okay, if I compare this, and you might say, how can you even say like this x is not significant? But if I compare x with x squared, it is insignificant, right? And I showed that graphically a few minutes ago, but I'll show it one more time. Y equals x goes like this. So over time, it's going like this. Y equals x squared, like it leaves x in its dust, right? Because it's going like this. So as time goes on, there's a huge difference between x squared and x. All right, so even compared with x squared, x itself is insignificant. So I would look at this and say, well, the most significant thing that I see here is this. Well, what does this reduce to? This reduces to simply 1 over x. And then if I think about the cookie concept, what if I have one cookie, right? So x over x squared reduces to 1 over x. Well, let's say I have one cookie and the number of people showing up is getting larger and larger and larger and larger and larger, right? How much cookie does everybody get? And everybody would get 0 cookies. Okay, so in the next segment, we're going to look a little bit more at what this means graphically as far as finding horizontal asymptote lines, and then we'll look at horizontal and vertical asymptote lines in general and do some exercises then with these limits to infinity. So thanks for hanging in there for this long video.